All right, good morning. So today we are going to largely wrap up a lot of the one and two sample hypothesis tests that we've talked about by covering tests of proportions and normality. Okay, so today we'll be covering hypothesis tests for tests of proportions and normality. As a reminder, our second homework assignment is due this Friday, and that will be working from the same data set that was covered in assignment one. So it should minimize the amount of time you'll have to spend getting the data prepared. And then the term paper lit review is due a week from Friday. And so I'll try to get you some feedback on the introduction in advance of that in the meantime. So that's what we have lined up for today. And so today we're going to talk about 5 specific types of tests. We'll cover 1 sample and 2 sample tests of proportions. And then we'll look at 3 different tests that can be used to assess normality or goodness of fit for other types of distributions. And that would include the chi-square goodness of fit test, the Shapiro-Wilk test, and the Kolmogorov-Smirnov test. Okay. And so to start with, we're going to start by talking about the tests of proportions. And you may recall that we had actually talked about this previously when we were looking at binomial distributions, because the binomial distribution has come into play in various aspects whenever we're talking about data that are proportions in nature. Okay. And so generally speaking, when we're dealing with a binomial, so anything that can be classified as a yes, no, or into one of 2 discrete categories, those data tend to be approximately normally distributed as long as NP is greater than 5. So here N is our sample size and P is that proportion. And so if we had a sample size of 10, and the probability of falling into a group of interest is 0.5. That's essentially the cut point. That would allow us to assume normality. And so generally speaking, when we're testing proportions, we'll rely on the standard normal distribution for our test statistic, as we'll get to in a few minutes here. Okay. And so for the binomial distribution, as you may recall, if we've got n number of trials, the average number of successes we would see in those trials would just be the sample size times whatever the probability is of us having an independent success in any one of those trials. And we're generally assuming that that proportion or that probability is going to be consistent from observation to observation. And we showed with the binomial distribution that the variance of that quantity is just going to be NP times 1 minus P. We'll also see that quantity 1 minus P denoted as Q in some instances. And likewise, the standard deviation of that number of successes is just going to be the square root of that quantity, NP times 1 minus P. Okay. And so keep in mind, we're using that when we have a set number of trials and we're trying to determine how likely it is we'd have X number of successes among those N trials. Now we can use that same rationale to basically look at probabilities or the proportion of outcomes within a sample that generate that same result of interest. And so if we wanted to just get P by itself, for example, in the case of a proportion, we're just going to divide each of those respective quantities by N. And so in the case of the mean, we just have our mean estimate is whatever that baseline proportion P is. The variance is going to be P times 1 minus P over N. And then lastly, that standard deviation is going to be P times 1 minus P over N, square root of that respective quantity, okay? And so those are what we're going to make use of today as we develop a large sample test for comparing proportions, whether that's 1 sample to 1 reference value or comparing proportions across 2 different samples, for example, okay? And so for the sampling distribution we're working with here, the mean of that distribution is just whatever that proportion P is equal to. The standard deviation is as shown on the preceding slide. Now, as is the case in most of the statistical tests that we conduct and have been introduced to in this course, we're generally not observing the whole population. And so as a consequence of that, we're not actually observing P. And so we would then need to estimate that quantity. And so the standard deviation of that sample quantity, the distinction here is just anytime you see a hat, that means it's an estimator for that specific parameter. And so in this case, we're going to take sample data that we're going to use to estimate P, and we'll denote the proportion within that sample as P hat. And so the standard deviation of our estimate P hat is going to be similarly the square root of P hat times 1 minus P hat over the sample size n, okay? And we're going to assume, and this is largely supported by empirical data, whenever that quantity n times P is greater than 5, that sample estimate of the proportion is going to follow a normal distribution, and the mean of that normal distribution is going to be P. And the standard deviation is going to be P hat times 1 minus P hat over n square root of that quantity, okay? And so from a hypothesis testing perspective, in a case of a one sample test, we're going to be comparing a proportion that's drawn from some sample data and assessing that versus some specific proportion of interest. A lot of times we'll just be interested in whether there's a preference one way or another, or if there's a tendency for yes or no responses in response to a question, as an example. And then we'd have the three different alternative hypotheses, either that there's a difference between our sample proportion and that reference value of interest, or we may have prior knowledge that would suggest that there would be a difference of interest in one direction or another. And so we would have either of those alternative hypotheses listed here as well. The underlying test statistic is just going to be a standard normal statistic. And so we'd take our sample proportion P hat minus that reference proportion of interest. You know, interestingly here, if we look in the denominator of this test, there are basically two different ways that this could be presented in concept. Either we could include the P hat here and use that in the standard error in the denominator, or we could include that reference value P naught. And you'll notice here, we're actually including the reference value rather than the sample proportion. And so does anybody have any thoughts as to why we would select P naught rather than P hat here? And I guess the hint I will give you is think about our assumptions going into these hypothesis tests. And specifically, if the null hypothesis is true, what would that mean about how we're calculating this test statistic? Does anybody have any thoughts on why we have P naught instead of P hat in the denominator here? Going once, twice. All right, I will handle this one. I'm going to come back with a very similar question in a couple slides if everybody's okay with that. So if our null is true, it basically means that there's no difference between the parameter we're evaluating based on that sample and the underlying reference value of interest. And so if the null is true, and that's generally how we set out with these hypothesis tests. We assume the null is true. And so consequently, P hat and P naught would be equal to one another if that were the case. We know what P naught is with certainty here. And so consequently, that's what we would then plug into the denominator here, because if in fact that null is true, then this would give us the most reliable estimate of what that parameter would look like, okay? And so looking at these quantities here, P hat, again, that's just the sample proportion. So we'd look at our entire sample and determine how many successes or how many yeses or however we parameterize that. P naught is just a reference proportion that we're comparing against, and then N is our sample size. And so this is the test statistic we'll use to evaluate comparisons for proportions. And just a quick note, as we had mentioned previously, this is an appropriate test if that quantity n times p is at least 5. In cases where it's less than that, we can basically just go back to the binomial distribution tables, and that's exactly what we had done in the prior lecture. So if we know the total number of trials, we can explicitly evaluate how likely it would be that we'd have a certain number of successes or failures. But as we get into larger samples, it becomes very cumbersome to try to go through and manually calculate that based on the binomial distribution. And so consequently, if we've got NP greater than 5, we generally would prefer to rely on this large samples test statistic. Okay. And so we would just compare the calculated values to our standard normal table, as we've done with a myriad of preceding tests. And everything is fairly similar and straightforward from there. And so at this point, we'll return to a similar research question we had investigated previously. And so let's say we've conducted a survey of 100 individuals, and we're asking them whether or not they're in favor of purchasing or leasing a self-driving vehicle. And we were told that the results show 66 of those 100 individuals were in favor, 34 were not in favor. And consequently, we're basically going to use the test of proportions to determine whether there's a significant preference within the sample, i.e., in this case, is there a lean towards being in favor of purchasing versus not, or vice versa. We're not particularly concerned in what direction that effect is, just whether or not there's a difference within that sample. Okay. And so consequently, with the setup here, our null hypothesis would simply be that our proportion is equal to 1/2 versus the alternate hypothesis that it's less than or greater than 1/2, just simply that it's different from that quantity, and we do have a lean in one direction or another. And so first of all, we calculate that sample proportion. So of those 100 individuals, 66 were in favor of acquiring a self-driving vehicle. And so p hat is equal to 0.66 here. And we can just plug those quantities directly into our test statistics. So 0.66 minus our reference value of 0.5. That same 0.5 is going to show up in the denominator here. And so interestingly, just as an aside, if we look at the variance of proportions, we'll tend to see the largest, well, we will see the largest variance when we have a proportion of 0.5 here versus in either extreme. If our proportion was 0.1 or 0.9, obviously we tend to see less variability within a sample if that were true. And so that's just kind of an aside here. We'll take that quantity, divide by our sample size of 100, and our calculated z-statistic in this case is 3.2. If we're assuming we're conducting this test at alpha of 0.05, we should hopefully all remember at this point that our critical values in the case of a two-sided test would be plus or minus 1.96. And so in this instance, we reject the null, and we do conclude that there is a significant preference in this specific sample. Individuals are more inclined to be interested in acquiring an autonomous vehicle versus not. Okay. And again, if you have any questions as we walk through, just feel free to type those into the chat box or unmute yourself. Similar to the one sample test, we can conduct a two sample test of proportions. The setup is quite similar here, except instead of just having one general sample of interest, we have two samples, which we'll denote with subscripts 1 and 2. And so our null hypothesis is simply going to be the proportion in sample 1 is equal to the proportion in sample 2. And as before, we'd have 3 different alternative hypotheses of interest to us, depending upon whether we had any prior knowledge or prior interest in terms of one direction of the distribution versus another. The test statistic, you'll notice here, looks quite similar to what we had seen in the one sample case. So we'll compare the difference between those two sample proportions, which are denoted as P1 hat and P2 hat. We'll compare that difference to some presumed difference of interest in those population parameters. And as a reminder, we're typically just concerned with whether or not there's any difference whatsoever. So we'd set that quantity to 0 and it would basically drop out of the equation. And then down in the denominator, our standard error is going to be the square root of p hat times 1 minus p hat times the quantity 1 over n1 plus 1 over n2. And so a natural question that arises here is, what is the difference between p hat and p1 hat and p2 hat? And so P1 hat is just the sample proportion in the first sample, so the number of successes divided by its respective sample size. Likewise with the proportion in sample 2. And then P hat, this quantity you see right there, is basically the average proportion across those two samples. And so we would just add the number of successes that we observed in sample 1 and sample 2, divide by the sum of those sample sizes, and consequently that would then allow us to conduct this test statistic. Now, with that being said, a natural question here is, well, why don't, an alternative way of setting this up would be to simply take P1 hat times 1 minus P1 hat all over N1 plus that same quantity for P2 hat times 1 minus P2 hat all over N2. And so the natural question that arises, and this is the chance to circle back to hopefully an answer from the audience here. So why do we use this quantity here, p hat, in the denominator? What's our rationale or justification, or why does that make sense in consideration of the way we've set this test up? Any thoughts? So if our null hypothesis is true, what's our prior assumption going in about P1 hat and P2 hat? Anybody?
So if
George?
our null hypothesis is true, then we are assuming that P1 is equal to P2. So the P hat will give us the same value as P1 or P2.
Thank you very much, Nishal. That's exactly correct. So the null hypothesis is that they're equal to one another. And so essentially P1 hat is equal to P2 hat is equal to P hat. And apologies if my audio just changed. I didn't realize that I wasn't using my AirPods at the moment there. So, okay. So that's the big picture setup here. We'll work through a similar example problem. So in this case, let's assume that we've conducted 2 samples of 100 individuals regarding that purchasing decision, and we'll assume that sample 1 is the same as was introduced previously, and 66 of those 100 individuals were in favor of acquiring a self-driving vehicle. And in the second sample, it was more split. In that case, 50 of those 100 individuals were in favor. And so we want to assess whether or not this difference in favorability is significant across those 2 respective samples. Okay. And so our null in this case is that those proportions are equal to one another, and we're just interested in whether there's a difference one way or the other across those samples. And so first of all, the proportion in the first sample, as was demonstrated previously, is going to be equal to 0.66. In the second sample, it's going to be 0.5. And so that's obviously very similar to the reference value we were comparing against in the preceding example. And our pooled proportion is how we'll also refer to this at times, is going to be equal to 0.58. And so consequently, we can plug those respective values into our standard normal test. And what we'll find then is that the numerator is 0.66 minus 0.5. The standard error of that estimate is the square root of 0.58 times 0.42, which is just 1 minus that same proportion, times 1 over 100 plus 1 over 100, which is 1 over each of those respective sample sizes. And then what we'll find in this case is that that test statistic, well, not as large as in the preceding example, it's 2.29. It's still is larger than our critical value, which in this case is going to be plus or minus 1.96. Ergo, we're going to reject the null hypothesis and claim that there is, in fact, a significant difference between those two samples, okay? And I guess one quick aside to note right here, so when we look at this quantity on the bottom of this test statistic, so this is the standard error of that difference in proportions. And so anytime you see poll results, and so just coming out of an election cycle, for example, you'd see plus or minus 4% or 3% or 6% error, depending upon what that sample size was. And so the way that's determined, basically, you would just take basically two standard deviations or two standard errors. You take that quantity, multiply it by 1.96 or by 2, and that's how those confidence intervals that correspond to the margins of error for those poll results are presented. So we use the same rationale here for the purposes of these hypothesis tests, okay? And so that was a relatively brief introduction into the test of proportions. I'm assuming many of you have seen those before. Do we have any questions on either the one sample or the two sample test at this point? Okay, hearing none. Next, we are going to continue on to talk about several different tests that are generally used to assess normality. Although these same tests can be used, generally speaking, to consider whether data sets follow any number of underlying distributions. And so the reason why this is important is that a large number of the tests that we've talked about up to this point in the course have operated under the implicit assumption that our data are normally distributed. And so we talked when we went through the non-parametric test last week about how when that's not the case, we could end up with some significant errors in the results of our hypothesis tests. And so consequently, it's important for us to be able to make a determination as to whether or not that assumption is a reasonable one. Now, informally, oftentimes, and this is very nuanced, it takes a while in working with statistics, but a simple way to try to assess this is to just try to look at a histogram of a data set. And what you'll generally be able to see when there are extreme departures from normality, so if your data is uniformly distributed or exponential or Poisson distributed, in those cases, it's fairly easy to see that they don't necessarily follow a normal distribution very well. But as an alternative to that, and particularly when that sample is small, it's very difficult to make that assessment just qualitatively from looking at a histogram or a probability density function. And so for that reason, we have a series of different tests we can use to explicitly evaluate using probabilistic methods whether or not those data are in fact well approximated by a normal distribution, okay? And so there are myriad tests that can be used to evaluate this assumption. There are at least 8 to 10 of these that I'm aware of. We're going to cover 3 in this course, and these are among the most widely used, and 2 of these 3 are actually explicitly included in SPSS, which we have access to in the engineering computer labs. And so that's one of the reasons why we're choosing to work with this specific subset of tests. And so we're going to spend the remainder of today's lecture basically introducing each of these tests and working through a few example problems, and then you'll revisit a few of these for the purposes of assignment 2. All right, and so when we're working with the chi-squared test, we're basically operating under the null hypothesis that our data follows some specific distribution of interest, okay? In this case, we're assessing normality, but you can basically apply this for any distribution of which we have known parameters, and we could determine a probability density function and a cumulative density function from. And so our alternative hypothesis in this case is simply that our data did not follow that specified distribution. And so this test is going to be somewhat unique in each of these tests that we'll talk about today, in that we're generally conducting these all as just one-sided tests, okay? So we're only concerned with the top tail of that testing distribution for the test statistic, or that probability distribution. And so what's particularly attractive about using the chi-squared is that you can apply it to any type of univariate distribution. We can also use chi-squared tests to assess model goodness of fit when we start talking about linear regression in a few weeks. And when we apply this test, we basically take our data and we develop a series of bins that correspond to the number of observations we would expect to fall within these specific bins based upon our prior knowledge and the characteristics of that distribution we're comparing against. And so we would compare how many values we actually observe within these specific bins or ranges of data versus how many we would expect to see. And the farther apart those observed and expected values are from one another, the more evidence we have that the data do not follow that distribution and that an alternative distribution may be more appropriate. Okay, it'll make a little bit more sense as we start looking at some real data here. But one important point to note at the onset is that this test is going to be very sensitive to the number of bins that we select. And so the size and the range of the values, if you think about how we could take a normal distribution and say break data into 4 or 6 or 10 bins, where those bins would basically be like histograms, for example. And so there's not necessarily an optimal choice. We do have some general rules of thumb, and that's that each of those bins should have an expected frequency of at least 5 values. So if you construct the bins too small, you'll often get some spurious results where you might reject this test simply because you've made the bins too small, for example. And so consequently, there's a little bit of art, a little bit of science here. The more you get used to working with this, it becomes more straightforward to apply. I should also note the test is not particularly good for very small samples. And so if you have counts that are less than, say, 5, as indicated here, you'd want to combine those bins. And so specifically, if you're looking at the tails of the distribution that you're trying to compare, you'd want to make sure that we wouldn't have values that are way out in the tails of the normal distribution, because it's so unlikely we'd see any observations in those specific ranges. Okay. All right, and so the formal test statistic that we're going to use right here for the goodness of fit test, we basically take our data set, we divide it into some number of bins, which we're going to arbitrarily denote as K here in terms of the number of bins. And with that being said, the chi-squared test just evaluates the squared difference between the observed and expected number of observations within each of those bins divided by the expected number of observations. And so this is basically giving us a sense of, it's a normalized squared difference of, you know, it's similar to some of the statistics we've looked at previously, where the larger that squared difference is, you know, the more evidence we'd have that our underlying assumption is a poor assumption. And so again, O sub I here is basically the observed number of observations that occur within a specific bin. E is how many observations we would expect to see based upon the properties of the distribution, like the normal distribution we'll be talking about today. And so we can basically determine that expected number by just going to our cumulative standard normal function, for example, and we'd select a value that corresponds to the upper limit and the lower limit of our data. And on that basis, we would know what proportion of that entire sample should fall within those bounds, for example, okay? And so this is likely best demonstrated through an example, which we'll get to in just a moment here. Now, once we calculate that test statistic, that statistic, as the name of the test implies, is going to tend to follow a chi-squared distribution. In this case, our degrees of freedom are going to be equal to K minus C. And here, K is going to be basically the number of bins or the number of cells that have values in it. And C is going to be equal to the number of parameters that define that distribution plus 1. And so, for example, In the case of a normal distribution, we know that the normal distribution is defined by its mean and its variance. So it requires two parameters for us to completely characterize a normal distribution. And so we add 1 in this case. So C is equal to 2 plus 1 or 3. And so what that means is that we would have at least 4 bins in order for us to formally conduct this test. And that would vary across different distributions we're interested in evaluating. So for example, the Poisson distribution is defined by just a single Poisson parameter. So in that case, we would only lose basically 2 degrees of freedom for conducting this test. And as I had alluded to, we're only concerned with the top tail of that distribution. And so in this case, if we're concerned with the top 5%, our critical chi-squared value would basically be the 95th percentile with K minus C degrees of freedom, okay? And that C term I'll also denote as being equal to P plus 1. So we could say K minus P minus 1 as an alternate to K minus C here, okay? All right, and so what we've got here, we have data given in the table to our right here that correspond to average travel speeds during the morning commute. These data were actually drawn from a real world study that was conducted in State College, Pennsylvania, where Penn State is located in the early 1980s. And so these are basically commute times from different areas in the State College suburbs regarding the average travel time. So this would include, you know, going through traffic signals. It's basically portal time. So the time it takes an individual to get from their home to their place of work in the morning. And that's why the speeds are a little bit lower here, because these people are dealing with congested conditions, a lot of travel time on surface streets, stopping at traffic signals and so forth. And what you'll tend to notice here, just from looking at these, the way these data are distributed, it looks like we've got a little bit of skew here. Obviously, there's a lot of data points clustered in the lower middle area of this distribution. And so if we were to look at this graphically, we basically see it looks like this. So just from a quick eyeball test here, you know, it looks kind of normal here, but then we see that we've got a fairly long tail on the right side. So we have a fairly high number of relatively large observations over here relative to where the bulk of those data are centered, okay? And so at the onset, we would have some suspicion as to whether or not these data are well approximated by a normal distribution, but we'll formally assess that by working through the test. And so again, the way this test works essentially is we're constructing bins in a similar nature to what we see right here. And we'd like to develop these bins based upon the properties of the distribution that we're interested in this case, the normal distribution. And so on the subsequent slides, we'll basically walk through how we organize these data such that we can apply the chi-square goodness of fit test, okay? All right, so to normalize the data, we're all familiar with how this works. We can just simply calculate the z-statistics. And so I've taken this sample of data. Our average travel speed across those 150 observations is 20.61 miles per hour, standard deviation of 4.85 miles per hour. And so from that, then we've seen this formula previously that we can use to normalize any random variable. And so in this case, using those sample estimates, we can normalize each of those individual observations. And so you see that column immediately to the right. And so that's the corresponding z-score for each of those specific speeds, given this sample operating under the assumption that these data are going to be normally distributed, okay? So this gets us part of the way to where we want to go. Now what we want to do is we want to determine how large these bins should be such that we've got a sufficient amount of data and can easily conduct the test. And so in this case, we're going to basically look at the standard normal table, and I thought it would be nice to basically break this in to 5 intervals. Okay, so we have 5 bins of data. The normal distribution, generally speaking, we're running from negative 3.4 up to positive 3.4, although the likelihood of us having observations on the lower end of this distribution or alternately on the higher end of the positive side of the distribution are quite small. And so what we're going to do is basically search the standard normal table for the value of z that will correspond to the 20th percentile, okay? And so we'll notice that that value is occurring right around 0.84. So hopefully everybody's with me here. And so our z-score of minus 0.84 would comprise the bottom 20% of a standard normal distribution. Likewise, we can use that same rationale to identify the 40th percentile. And so that's occurring down here at minus 0.25, you'll notice. And so that's our 20th and our 40th percentile. We know the normal distribution is symmetric. And so though I've omitted it here, the 60th percentile would just be the positive number here, 0.25, and likewise the 80th percentile value would be 0.84, okay? And so having established those 4 cut points, we've now basically developed thresholds so that we have 5 bins that are actually of equal size in this case. And so from that, we can basically, there's several different ways we could approach this. We could just take the standard normal values we've already determined, or we could back calculate and figure out what range of the actual speed values would define those same bounds. And I've introduced it both ways here just to make this a little bit more intuitive for everybody following along. So for example, we can solve directly for the speed value that would correspond to that 20th percentile if those data were normally distributed. And what we'll find is that would be 16.54 miles per hour. So we'd expect that 20% of the observations would be less than or equal to 16.54. And likewise, the other cut points would be 19.4, 21.82, and 24.68. Okay. And so we know what our bins are now in terms of both the z-scores and the actual measured speeds in miles per hour. And we've structured these such that those 150 observations, 20% would fall within each of these respective bounds. And so our expected values, or our E sub i's, are going to be 30 in each of these cases, okay? From that, we can also overlay our observed number of observations within each of those categories. And as you can tell from looking at the way the data are distributed here, we have some fairly substantial deviations once we get beyond that first bin. And so we're going to work through bin by bin here and calculate the individual contributions of each of these for that chi-squared statistic. And so as a reminder, the way we conduct this test, we're basically going to take each of our 5 bins, or each of our K bins, and we're going to take the observed number of observations in each cell minus how many we would expect to see. So 24 minus 30 as an example in the first case. We'd square that quantity and divide by 30. And we'd repeat that same procedure for each of the 5 bins in this case, as you can tell, based upon the underlying formula. From that, we calculate our chi-squared statistic of 74.47, and then we want to be able to compare that to the upper tail of our critical chi-squared distribution. And though you may not have had a lot of experience working with chi-squared tests up to this point, that is a quite large value, especially for a small sample, as we see in this case. And so as you'll recall, we're going to have K minus C degrees of freedom. And so we know that the normal distribution, again, has 2 parameters. We're going to add 1 to that. So we're subtracting 3 degrees of freedom from our size of 5 bins. And so our critical chi-squared value for the upper 5% of that distribution with 2 degrees of freedom is going to be equal to 5.99. And so our calculated test statistic is well beyond our critical value. And consequently, in this instance, we're going to reject the null hypothesis and claim that these data do not appear to be well approximated by a normal distribution. Okay. And so that is basically a quick introduction to the chi-squared test. I know that many of you that have had traffic engineering classes have probably seen something similar to this. We can actually use a similar type of approach if we wanted to revisit the test of proportions that we had seen in the preceding example. So in that case, if we were just testing against a proportion of 0.5, we could have just created 2 bins, for example, right? And we would know how many observations we would expect to see within each of those respective bins. And so there are other different variants of that. Basically, anytime we have prior knowledge of how many observations should fall within specific ranges, based upon the assumed underlying distribution, we can assess whether or not the data we're actually observing are well characterized by whatever that fundamental model or distribution would look like. Okay. All right, so that's the first example. Now, as I had noted, the chi-squared test is a relatively nice test, straightforward, easy to conduct, but it runs into problems when we're dealing with small sample sizes. And so to that end, there is a fairly good test for those circumstances that was developed by Shapiro and Wilk, which involves the calculation of what we'll introduce as a W statistic. And so that allows us to, again, explicitly assess. This test is tailored specifically towards normal distribution. So as opposed to the chi-squared, we're only using Shapiro-Wilk to assess normality. And in this case, in contrast to a lot of the tests that we've talked about up to this point, rather than large values, we're concerned with small values of W are evidence that we're departing from our normal distribution. And in this case, there's not a nice, easy set of critical values for this. And so there's work that was conducted back in the early 70s, which has resulted in the tables that are used for the implementation of this test. A lot of these have been integrated explicitly into statistical analysis software. And so the manual approach we're going to introduce right now over these next few slides is limited to samples between just 3 and 50. Once you get beyond that, this test has been built into standard software programs. Just frankly speaking, it's very laborious to try to conduct this manually in those larger sample sizes. So fortunately, for the purposes of the homework, we do have some fairly large samples, at least when we're combining the speeds of all vehicles, for example. And so consequently, you can use SPSS or other programs to conduct the Shapiro-Wilk in those instances, for example. Okay. And so the Shapiro-Wilk test, the W statistic, is calculated as shown here. So what we basically do, we take all of our samples and we sort them in ascending order from smallest to largest. Okay. And then for those individual observations, we pull some constants that have been generated based upon the means, variances, and covariances for a sample of size n from a normal distribution, okay? And what we're essentially evaluating here is how the ranges of those values that we observe correspond to what we would expect to see with the normal distribution. And so depending on the sample size, this coefficient A is basically measuring how closely our observed X's are falling with respect to where they should if we assume those data are normally distributed, okay? The denominator here, we generally refer to this, and we've seen this previously, this is our sum of squares. So this is the denominator in this test is the same numerator we would see in our variance or standard deviation calculations. We take each individual observation, subtract the mean, square that quantity, and sum across our samples, okay? And so in terms of conducting the test, our process is as follows. So like I said, we're arranging the data in ascending order. We're then going through and calculating our sum of squares. And then we're determining where the median point lies. So we're going to define that as m here. If our sample size is even, we're going to let m be equal to n over 2. While if n is odd, we're going to set m equal to n minus 1 over 2. And it will become evident in a minute why we're doing that. So this m is basically corresponding to the number of those coefficients. So the A that was introduced previously. We can also think of M as the number of pairs of data points that we have in our sample. So if we have an even number, the pairs of data points is just the sample size over 2. And in the case of an odd number of observations, that's not the case. So we correct for that by subtracting 1 from the numerator here. Okay, so we've paired the data, and then we're going to calculate a statistic that's noted as B. And what B is doing, it's not evident necessarily from the first time you look at this, but what we're going to do, we're going to take the largest observation in our sample, and we're going to subtract the smallest observation. We're going to take the second largest sample, and we're going to subtract the second smallest observation from that sample, the third largest value, subtract the third smallest value. And so as I talk through that, it probably helps this nomenclature to make a little bit more sense. So as we increase I from x1 to x2 to x3, it would be basically our largest observation plus 1, minus 1 or 2 or 3. So those are basically converging towards one another. So as an example, if we had a sample of size 100, we would have x1 here, and then we would have 100 plus 1 minus 1. So this would be our 100th or our largest sample. If this were x2, we would be taking the difference between x99 and x2, x98 and x3, and so forth and so on, okay? And so that A coefficient I had introduced previously is just basically corresponding to, for each of those individual observations, it's quantifying how important those differences are. So in the case of a normal distribution, we have a good sense of how variable, how large this quantity should be in a relative sense for a sample of size n. And so A is basically serving as a weighting factor here. And so we're applying greater weight to greater departures from normality in those instances, okay? And so we sum this across each of those pairs of observations within our sample. And our W statistic is just going to be this quantity B squared divided by our sum of squares, okay? And so once we've calculated that value, the critical value is going to be taken from a Shapiro-Wilk table, which again was developed back in the early 1970s. And from that, we can directly determine the p-value and or the critical value that we're using for comparison purposes here, okay? And so I'd say among the tests we're going to cover, this is the one that's probably the most important to work through an example on, just because it's not necessarily straightforward at first glance. Now those coefficients, the A sub i's, as I had mentioned, we're basically looking at differences between pairs of observations. So differences between the largest and smallest, and working our way in until we get to those observations in the middle. And so what we see here, I had noted previously that that quantity M is just equal to N over 2. And so M is basically representing the number of A parameters of interest, okay? So in the case of a sample size of 2, we would have just one difference. In the case of sample size 4, we'd have 2 differences. In the case of a sample size of 6, we'd have 3 differences. And then you'll notice for the odd number categories here, the middlemost observation, the median observation, we don't have another value to compare it to. And so that basically is just discarded for analysis purposes, okay? And so we use this same series of coefficient tables, and this will range all the way up from a sample size of 2 up to a sample size of 50. So I'll just click through these really quickly for each of you, culminating here on this last table that runs all the way up to a sample size of 50. And so obviously in the case of a sample size of 50, we'd have 25 differences. And so that's where we'd have 25 coefficients, okay? And so you can see with respect to scalability, it becomes much more laborious in order for us to calculate this manually with larger samples. But fortunately, this functionality has been built in to a lot of our standard statistical software applications, okay? Now, likewise, our p-values and our critical values for the test can be evaluated directly here. Now, as I had mentioned previously, the critical values here, we're rejecting test statistics that are small rather than test statistics that are large. So as we're reading this table, we're concerned with this 0.05 column that you see right here. So if you have values that are less than these critical values, we would reject at 95% confidence, okay? And so these values you see up at the top would basically be corresponding p-values. And so if you had a sample of size 10 and your calculated test statistic was 0.842, that will correspond to a p-value of 0.05. And we can interpret it that similarly as our calculated test statistics get larger, our p-values, of course, are getting larger in those cases as well, which is in contrast to a lot of the other test statistics we've looked at up to this point, okay? And so now let's work through an example. We'll return to a data set we had introduced previously. So you'll recall we've been working with crash data at these series of 10 intersections that had some signal timing changes introduced. And so since we've conducted a number of parametric tests here, it would probably make sense for us to circle back and assess whether or not these data in fact follow a normal distribution. And so we're going to do that. For the sake of time, we're going to work through this example just for sample 1. I'll leave sample 2 as an exercise for you to work through on your own. And so with sample 1, the first thing we're going to do, as I had noted, is we're going to sort our data in ascending order. And so in this case, I should note the I's are different than what we had seen in the preceding slide. In this case, it just relates to the ordering. So our smallest observation is x sub 1I, which is 5 in this case. Our largest observation, x sub 1, 10, is going to be equal to 14. And with this, we also want to determine what our A values are. And so in our instance, we have a sample size of 10. And so we would have 5 A values that we're going to use for our subsequent calculations once we pair and take the differences between those pairs. And we can also calculate the sum of squares for these quantities here. And so I'm just taking each of these individual observations, subtracting the mean, squaring that quantity. And if we sum that across all 10 observations, our sum of squares for this case is 69.60. Next, we are going to pair the data. So as I had mentioned, the highest and the lowest. And so this is the 5 largest numbers in descending order and the 5 smallest numbers in ascending order. And so we can take the differences between those quantities. And so the next column shows those differences range from 9 down to 1. And this is what you would expect to see. Obviously, you'd see the largest difference for the first quantity, and those will gradually converge towards a number that's going to be close to 0 as we approach the median of the distribution. We're then going to take our coefficients A that were introduced previously and multiply those times the difference. And so here we basically see those A coefficients, A times these corresponding differences. And we're going to take those quantities and we're going to sum those up, and those will end up summing to 8.208 in this case. Our W statistic is just that quantity B squared divided by the sum of squares that we had presented on the previous slide. And so 8.208 quantity squared divided by 69.60 gives us a W statistic of 0.985. We would then compare that to our critical value. And so keep in mind, in this case, we had a sample size of 10. We're interested in a significance level of 5%. And so our critical value is 0.842. We compare to that critical value. If we're less than 0.842, we would reject. As it turns out, in this case, we're significantly larger than that value, and consequently, we cannot reject. And so for this sample of size 10, we don't have any reason to strongly suspect that that normality assumption is a poor assumption. And so it seems like it would be fair for us to use any of the parametric tests we have talked about up to this point in the course. Okay. Any questions on the Shapiro-Wilk at this point? We can circle back at the conclusion of the lecture, but okay. So the next test we'll talk about is the Kolmogorov-Smirnov test. And so this is another test that allows us to assess normality. We can also use this to assess goodness of fit versus a wide range of other families of tests, so not just normal distributions. And it allows us to either assess whether an underlying distribution fits some specific parametric distribution of interest. It also allows us to compare whether two distributions are similar to one another. So sample distributions, for example, whether the sampling distributions are the same or not. And so in concept, what we're doing here basically is we know what the cumulative density function looks like for, say, a normal distribution. And we can construct an actual observed distribution based upon our sample of data. And so that's what's being approximated in the blue here. And what we're doing in the Kolmogorov-Smirnov or KS test is we're observing the differences between that expected hypothetical distribution and the observed distribution that's based upon our data. And so the larger these differences are, the poorer the fit for that specific distribution. And so we're going to base the determination here on whether a specific distribution is appropriate or not based upon how large those differences are. Okay. And so in the specific case of the normal distribution, as illustrated on the preceding slide, we can standardize our variables, compare them to that standard normal distribution. And that's just basically analogous to taking the mean and variance of the reference distribution and setting them equal to whatever our sample estimates are, okay? And so in this case, when we think about our hypotheses of interest, our null is basically that the sample or samples that we're analyzing come from some distribution. We'll just arbitrarily denote that as P, versus the alternate hypothesis that they don't come from P, they come from some other distribution. We're not particularly interested here in what that alternate distribution is. We're just determining that it's different from P, for example, okay? And so the KS statistic itself is basically just whatever the maximum distance is at any point along that cumulative density function for those two distributions, okay? And so the general process, and similar to what we've seen in a lot of these other cases, we're going to take each of our individual observations and we're going to determine how likely it is that we would observe that value of X, for example, given that our data are following a normal distribution, okay? And so, like I said, in this case, we're assuming a normal distribution, so we can just go directly to the standard normal table that we're all quite familiar with. But we could use a similar approach for other types of distributions, and you could go to the corresponding tables and tabular summaries for those distributions to analogously conduct the KS test for those other types. With that, we would also be interested in determining basically our probability of observing that specific value within our own empirical or sample distribution here. And all we do in that case, assuming our data are sorted in ascending order as we had done in the previous tests, for each individual observation, that will just be our quantity I, so our observation number from 1 up to n divided by the respective sample size, okay? Pardon me. And so what we're going to do then is calculate the maximum absolute difference between those expected and observed distribution functions. And that's illustrated graphically right here. So for each one of our data points, we know what the normal distribution looks like. We know what the distribution of our observed data looks like. So we've taken each of our data points and we've normalized it. We subtracted the mean divided by the standard deviation. And that plot looks as follows. And so the differences here are basically those distances that are denoted in green. So we're just taking F expected minus F observed, or vice versa. We're just concerned with the absolute magnitude of those differences in this case. And whichever of those is the largest difference is going to be our Kolmogorov-Smirnov statistic. Okay, so the maximum value of any of those observed differences. Okay. And the critical value, interestingly in this case, is going to be determined just from this simple equation where we take 1.36 divided by the square root of the sample size. Okay. And so what that means in concept basically is that as our sample size gets larger, we're going to reject based upon smaller differences. As compared to a very small sample, we don't have as much precision or as much reliability in those cases. And so in those instances, we're going to require a larger difference between those distributions observed and expected in order for us to reject the null. All right. And so we're returning back to the average travel speed data for the commute into State College, Pennsylvania. And so we have the same distribution of data that we had worked with previously. We first of all compute the theoretical or expected distribution. So like I said, we're working with the standard normal in this case. And so I basically just went into Microsoft Excel and developed a standard normal curve from -3 to +3. And then from there, we have our empirical distribution based upon our data. And so in this case, like I said, the process is just you take each individual observation and its probability is just essentially equal to 1. Its value, its ranked value from 1 up to n with respect to the total sample size. And so in our case, the first observation, the speed of 14 miles per hour would correspond to the 0.007 would be the proportion or the probability within that larger sample. The second observation, and we'd have 22 of these value 15s, as you can tell from this very large vertical line here, would correspond to 0.013, and we would increase that for each of these 22 observations. So you see that's consistently increasing. And that'll tend to happen here. So the shape of our distribution, if we're dealing with just integer values, as we see here, we'll see a series of step functions like you see right here. If our data were measured at a finer level of fidelity, so if we went to the fraction of a mile per hour, which we actually could in this case, I just changed things to make things a bit simpler for us to work through. We'd see more of a smoother distribution here, but this is just hopefully giving you a sense of what that observed sample of data looks like. And so what we're doing ultimately, we're comparing this distribution of observed data to what we would expect to see from a normally distributed data set, which would be, the S curve that was denoted on the preceding slide. And so to calculate and conduct the KS test, we're basically just taking the differences between those observed and theoretical distributions. And so here I've overlaid them upon one another. And so we're basically calculating all these differences for each of the individual data points, and then just identifying where that maximum value occurs. And so I won't go through full calculations here, but for the first 3 observations, as an example, we have our observed cumulative density function score. We have our expected cumulative density function score for that first observation. You'll notice it's a relatively large difference for this point. And likewise for each of the 2 subsequent points as well. And then we'll see we start converging back towards normal in this range, and then we get some relatively large departures again. And so we're evaluating that difference, or the absolute value of that difference, across the entire distribution. And what we'll find ultimately is that that largest difference is going to be equal to 0.21. We take that 0.21 value and we compare that to our critical value, which as per our formula is going to be a difference of 0.11. And so in this case, our observed data show a calculated KS statistic of 0.21, which is greater than our critical value. And thus we can reject the null and claim that our data are not normally distributed. Okay, so we basically came to the same conclusion here that we did for the chi-squared goodness of fit test, but just using a slightly different metric. Okay, and so generally speaking, with any of these tests, they're typically going to give you the same ultimate conclusion. There'll be some subtle differences depending upon things like our sample sizes, and particularly at smaller samples, we'll see more divergence. But any of the three tests we've introduced today would all be alternative ways for us assessing that normality assumption, which is underlying to many of the hypothesis tests that we're evaluating over the course of this class and in applied statistics generally. Okay. And so with that, that wraps up everything I had for today. So you're equipped with all the knowledge you would need to conduct the second homework assignment. I'm also going to post a very quick tutorial video for SPSS to get everyone familiarized with how to run some of these tests in that software program. And then when we return on Wednesday, we'll talk about confidence intervals. This is an area you should be quite familiar with if you've had any prior experience with statistics. We won't cover confidence intervals to nearly the level of detail as hypothesis tests. There's a natural parallel between the two. They're used in analogous circumstances, just slightly different contexts. And so we'll talk a little bit about that and probably wrap up most of that discussion this week. And then, like I said, assignment 2 is due on Friday, and the term paper lit review is due a week thereafter. And so with that, I am going to basically bring it to a close